Let's find the arc length of some function. Imagine we have some function, then we plot some points in the function. If we join those points with a chord, we see that the length of this chord is different from the length of our function. But if the number of points in the function goes to infinity, we see that the length of our function approaches that of the length of all the combined chords. Now let's focus on a single chord. We call this chord ds. We see that the chord is the hypotenuse of a triangle with base dx and height dy. Then by the Pythagorean theorem, we see that ds is the square root of his sides squared next. If we factor dx out of the square root, we get this form expressing arc length in terms of the square of the tangent. Therefore, the integral of all of those tiny chords is the total arc length of our function. Let's talk about surface area. Imagine we have some cone of radius r and side length l. Then we cut the cone and stretch it. We have a section of area A and base 2pr. We can imagine this section as the part of a circle. We notice that the ratio of the area of the sector with respect to the area of the circle is the same ratio as the ratio of their circumferences. If we solve for A, we get PRL. Remember this formula for later. Imagine we have a cone split into 3 parts. We are trying to find the surface area of the yellow part that's called a frustum. First, we see that by similar triangles, the ratio between the side length of our top cone L2 and its radius R2 is the same ratio as the side length of the whole cone L1 and his radius R1. So we reach this form. Next, we are going to find the surface area of our frustum. To do that, we are going to subtract the surface area of our whole cone minus the area of our top cone. Next, we factor pi in this equation. Now we add our second equation. We can do that because his sum is 0. Next, we factor R1. Next, we factor L1 minus L2 out. Next, we multiply by 2 halves. But L1 minus L2 is the side length of our frustum, and R1 plus R2 over 2 is the radius of our frustum. So the area of our frustum is L2 PIR. Next, imagine we have a function. If we rotate this function around the axis, we get a frustum. But now imagine a tiny frustum with side length ds. But remember, the surface area of a frustum is L2 PIR. In our tiny frustum, the side length L is ds, and the radius is just f of x. So if we integrate all of those tiny frustums, we get the total surface area of our frustum. But remember, ds is a tiny chord that we express in terms of the derivative of the function. Conclusion. We say that the surface area of any function is the integral of all of our tiny frustums, with the side length of our tiny frustum being ds, and the radius of our tiny frustum being f of x.